Welcome to the walkthrough of the 2024 GCSE Physics Paper 1, and we're looking at the higher tier paper today. So the first question is showing us a picture of a wind turbine, and wind turbines may generate electricity when the electricity is not needed. We've got two different methods. We've got method A of heating water to a high temperature and method B of pumping water uphill into a reservoir. Now our first question is which energy store increases when water is heated? Now we're looking at either the thermal store or the internal energy. You could also talk about the kinetic energy of the water particles, but thermal or internal stores probably the best answer on that one. And then 1.2, which energy store increases when water is pumped uphill into a reservoir? Bit of a clue, uphill. So it means that our gravitational potential energy. So we're increasing the height of that water, therefore it's gravitational potential energy store. And there is your mark. Now, question 1.3, we're up to a full marker straight off. So we've got a table of information with information about the two different methods of storing energy. So we're looking at method A, which is increasing water temperature by 80 degrees centigrade, and comparing it with pumping water uphill to a height of 500 meters. Now, for 4 marks, we need to compare the advantages and disadvantages of the two methods of storing energy. And it's saying include calculations in your answer. Now, for you to reach level 2, which is either 3 or 4 marks, you need to be using relevant calculations to compare the two methods. So if there's no calculations in your answer, you're limiting yourself to a maximum of 2 marks. Now, in terms of it's disadvantages to method A. Now, if you heat water to that temperature, you're going to need to insulate the material. So that's going to add a bit of cost to this. Now, if you look at the data in terms of comparison, the advantage is there's an awful lot more energy stored in the hot water. You know, you're looking at 33,600 kilojoules. That's a lot of energy. So then, and that's per 100 kilograms. Now, useful energy from heating 100 kilograms of water. Well, if 40% of the energy is wasted, it means that just over 20,000 kilojoules is used usefully. However, 40% of your energy is wasted. That works out at about 13,400 kilojoules. So the efficiency is only 60% with method A. Now, if you compare that with method B, one of the drawbacks is that you need a suitable location to actually pump the water uphill. You can't just do that anyway. On the plus side, the advantage is that this method is 75% efficient. Only 25% of your energy is wasted. Then when you do the maths on it, the useful energy per 100 kilograms of water works out about 367.5 kilojoules. So like I said, 75% efficient, which is quite impressive. Which means, on the flip side, the energy wasted is only 122.5 kilojoules. So we're talking 75% efficiency. So that's where you've got your comparison. So it doesn't really matter which method you say is better. There's more energy stored in the water. However, storing the water uphill is 75% efficient. You just need to make some balanced views and remember to include your calculations to make sure you're getting into that 3 or 4 mark kind of category. Right, and then 1.4, decreasing the amount of carbon dioxide released by different activities will help slow down climate change. So transport and generating electricity are two of the activities that release large amounts of carbon dioxide in the UK in 2018. So here we're being asked to explain one change that would reduce the amount of carbon dioxide released by each activity. So there's 4 marks here. So there's going to be 2 marks for transport, 2 marks for generating electricity. In a way, you'll get 1 mark for giving an idea of what you could do, and then a second mark would be to explain the impact of that change. So in terms of transport, it would be don't use petrol or diesel cars, or at least reduce the use of. So you could do that. You could cycle, you could walk. Don't forget, you could also use things like electric cars. Even hydrogen fuel cars would be fine. Also, don't forget about public transport. So that has less of an impact, and the reason for it is that we're not burning or we're reducing the amount of fossil fuel that we're burning. So we're not burning fossil fuels, which means we're releasing less CO2, so it's having less of an impact on climate change. In terms of generating electricity, we just don't want to be generating electricity using our fossil fuels. So don't use, remember, coal, oil, or gas to generate electricity. Look at alternative methods. So you've got all your renewable forms, so whether you use wind turbines and so on. You could also use nuclear fuel. So although that is not a renewable source, it doesn't produce any carbon dioxide, so it's going to reduce the impact of kind of climate change. Other thing you can talk about is don't use electrical appliances when not needed. So that would be another way. And again, it just means that less electricity is being used, therefore less carbon dioxide is being released into the atmosphere. So make sure you've got a valid point for each for transport and for generating electricity, give an explanation of why, like the repercussions of it. Right, that first question is worth 10 marks. Well done if you got all 10 on that. Right, so question 2. We're into the process of nuclear fission, and this is used in nuclear power stations. So we've got an example of nuclear fission with a diagram below. Now we need to fill in the blanks, and we're even given the words that we need. So this is quite a generous question. It's worth 3 marks. In a nuclear power station, energy is released from the uranium. Comes from the nucleus, so uranium nuclei. So in figure 2, our uranium nuclei splits into 2 parts, and it releases, well, those black dots are neutrons. And then the process of nuclear fission releases electromagnetic radiation. I know electromagnetism is part of paper 2, but you should know in this case it's in the form of gamma rays. So it's a form of good old gamma. All right, nice 3 marks for that one, very generous. Now, next one, this probably should be the easiest mark you're going to get on your paper. Write down the equation which links energy, power, and time. Now, bear in mind you're going to have the formula sheet. I couldn't make it any easier for you. So energy equals power times time. You can also write the symbols. E equals PT. Easy mark. And then of course, next question is using that formula to answer the question. So a nuclear power station has a power output of 500 milliwatts. Calculate the energy output in 3,600 seconds. We need to give our answer in joules. So we're going to end up with a big number because we need to be suspicious here. This is a 3 mark answer. We've got to work out the amount of energy. Bear in mind, energy is power times time. Now, you should be suspicious, thinking, we're just going to multiply 2 numbers together. There's got to be more to it to get my 3 marks. And hopefully you're a bit suspicious because that 500 milliwatts needs converting into watts. Now, so not milli, it was mega. Capital M means mega. Mega means we've got 1,000,000 of them. So we need to convert 500 megawatts, I should say, into 500 million watts. And then put your numbers into the formula. E equals our 500 million times 3,600. So 1, and that's multiplied by 3,600. Right, plug those numbers into your calculator. And there's two ways you can answer this. Your calculator might bring it up as standard form. So you can say 1.8 times 10 to the power of 12, or write it out as a full number. So you got 1800, and then we've got 9 zeros following. Just be really careful with your zeros when you're writing this down. You're going to lose a mark if you do a power of 10 mistake. Essentially, that's what they talk about. So be really careful writing out and showing you're working out. Now, question 2.4. Radioactive waste produced by nuclear power stations has a long half-life. Suggest one precaution taken to reduce the hazard caused by radioactive waste from power stations. Now, there's only one mark, so you only need to come up with one idea. So you could bury the radioactive waste. You could put the radioactive waste in cooling ponds. You could transport the radioactive waste in secure vessels. It doesn't say where you're going to take it to. Store the radioactive waste in metal containers. Cover the radioactive waste in concrete. So anything along those lines is enough to get you the mark there. And then finally, we just got another maths question. And to be fair, you don't actually need to know that much science to be able to work this one out. So nuclear power stations do not generate electricity every day of the year. So one nuclear power station generated electricity for 92% of the year. It even tells you how long a year is, 365 days. Calculate the number of days during the year that the nuclear power station generated electricity. Well, it's 92%. This is really a maths question. Do you know what a percentage is? 92% just means 92 parts out of 100. So you've got to do 92% of multiplied by 365. And that's going to give you an answer of 335.8 days. Now, it doesn't matter if you round that up to 336. In this case, an acceptable answer is also 335. But don't worry about the fact that there's a percentage there. 0.8 of a day is absolutely fine. That question's worth 10 marks, so well done if you got all 10. Right, moving on to one of our required practicals, and I'd like to think this is one of the more straightforward required practicals because you certainly do it lower down the school. So here we've got a student that investigated how the length of a wire affects the resistance of the wire at constant temperature, and it's showing you set up very clearly of the equipment that you're using to carry out this particular investigation. So the student plotted a graph of resistance against the length of the wire. Describe a method the student could have used to collect data to plot the graph. Now, obviously, to get a level 3 answer, you need to come up with a method which would produce valid results. You've got to identify all the key steps, and it needs to be in the right order. Now, first thing, I would start off with measure the length of the wire between the crocodile clips using the ruler. I'd generally start off at 10 centimeters of length. Then you need to be talking about how, once you've taken your readings, you would then move to 20 centimeters in length, 30, 40, 50, 60, 70, 80. I'd go all the way up to 100 centimeters. You would talk about the fact that the current is being measured by our ammeter, which is this bit up here, and that the potential difference is measured with our voltmeter kind of here. We then would take the readings at 10 centimeters length of wire, 20 centimeters, 30, so on. You'd be taking the readings off the ammeter and the voltmeter. Record your results in a table. You would then calculate the resistance, and remember to include how to calculate that resistance. So you need to include our formula, V equals IR. And from there, The other things, standard things with required practicals when you have to write a method, talk about taking repeat readings at the different lengths, so that you can calculate a mean, discount any anomalies. Now, one of the things it's worth adding in here, and it doesn't ask about the safety side of things, but we do need to control the temperature. So we need to make sure that our current is relatively low, or is low to reduce heating of the wire. In part, that's why we've got the resistor in the circuit, but also what you would do is you would turn off the power pack between readings, and that reduces the chance of the wire getting hot as well. Now, to get that into at least level 2, you've got to talk about how you vary the length of wire and also how you measure potential difference in current. To get the full into level 3, the full 6 marks, you need to have that full method just as I've described. Key thing which often gets forgotten about is don't forget the formula is important in this, in how to produce the results, because remember the question is asking you, how did the student collect the data? Well, you can't plot the graph without having worked out the resistance, so don't forget about that bit. And then 3.2, we just need to work out which is the correct graph. Now, we're keeping the temperature constant, so what happens as the length gets longer, the resistance increases. And in this case, the relationship is direct proportionality, which means that we're looking for a graph that starts at the origin and is a straight line. That bottom graph is the one that fits the bill. Now, on question 3.3, the student used a cell that had a potential difference of 1.5 volts. Explain why the cell was not an electrical hazard to the student in the investigation. Now, first of all, make the comment that the potential difference is very low, which means that therefore, I'm just going to use that sign for abbreviation, there's no risk of electric shock. So remember, this is worth 2 marks. So it's not just a case of making 1 point, we need to be making 2 points. So we can either say there's no risk of electric shock or there's no risk of electrocution. Either way, you get that 2nd mark. Now that question's out to 9 marks. Well done if you got 9. Alright, so now looking at static electricity on this one. And you've got your Van de Graaff generator, which probably most of you are familiar with, and the rubber belt is turned by a motor. As the rubber belt moves, charge is transferred from the rubber to the metal dome. Now in question 4.1, we've got the diagram of somebody using the Van de Graaff generator, and it shows a student touching the metal dome of the static electricity generator, and the dome is negatively charged. Explain why the student's hair stands up on ends. Now, this is the important bit. Remember, with static, it's the electrons that move. So electrons are transferred from the dome, transferred to the student. Now, this means her hair is negatively charged. So if all hair is negatively charged, like charges repel, meaning that her hair is trying to get away from the hair that's next to it. That's why it stands up on end. And there's your 3 marks. Right, so question 4.2, what is an electric field? Now, this is just one of those definitions that you just need to know. So it is the region around a charged object where another charged object experiences a force. So this is one of those definitions, you just need to learn it. There's no two ways about it. Now, question 4.3. How does the electric field strength vary as the distance from the charged metal dome increases? So as we're moving away from the metal dome, what's going to happen to the electric field strength? Well, it clearly decreases. Why they need to give you 2 lines of space for that, I don't know. One word will do the trick and get you the mark. And then in this next question, great question, is worth 4 marks, nice maths one. So we've got our negatively charged metal dome and we've got the earthed conductor. So when the earthed conductor is moved towards the metal dome, there is a spark between the dome and the earthed conductor. So remember, our spark travels across and it always looks very impressive. Now the spark transfers 0.6 joules of energy and 2 microcoulombs of charge is transferred from the dome to the earthed conductor. We need to calculate the potential difference between the metal dome and the earthed conductor. Now this is worth 4 marks, so we should be a little bit suspicious. Now hopefully the bit that stands out here is the fact that we've got 2 microcoulombs of charge. Now that's clearly shouting out that it needs converting. We need to convert it into coulombs. So micro means a millionth. So it means that our 2 microcoulombs equals 2 times 10 to the power of minus 6 coulombs. So it's a millionth. So divide by a million. You can use this as standard form or just use it as a long decimal. Now we've got to remember our formula. Energy is charge multiplied by potential difference. So in this case, we've got to calculate the potential difference. We've got the energy and we've got the charge flow. Substitute in the numbers that we've got. Now, we've got 1 mark for the conversion alone. Substitute the numbers in. We've got 0.6 equals 2 times 10 to the power of minus 6 multiplied by V. That's where we get our second mark from. And of course, the third mark is from doing some manipulation. We need to get V by itself, so we need to divide both sides by the 2 times 10 to the minus 6. So 2 times 10 to the minus 6. Put those numbers carefully into your calculator and you're going to get a value of 300,000 volts. So where do the marks come from? 1 mark for the conversion, 1 mark for the correct substitution, 3rd mark for making the potential difference, V, the subject, and then the 4th mark of getting 300,000 volts. That clears up all 4 marks. Now, if you don't use the conversion and you use the value of 2 all the way through, you're going to be out by a factor of 1 million. You only lose 1 mark from doing it. So even if you don't convert or you convert incorrectly, you still can achieve 3 marks on that particular question. And then question 4.5. Which of the following changes would increase the distance a spark can jump between the dome and the earthed conductor? Now, a decreased charge means we've got a smaller potential difference, so that's going to be 0. Decreased electric field strength, not going to be to do with that. Decreased potential difference, again, less energy. The answer that stands out, if we reduce the resistance of the air, that's going to cause our spark to jump further. So that is your only option on that particular question. So it's the 3rd box down. That question's out of 10. Well done if you got 10 out of 10. So on to question 5. So the figure shows a coin being put into a vending machine that sells food. Now the question is all about the fact that the vending machine is connected to the mains electricity supply. There are 2 numbers you need to know about mains electricity, and that's what this question is asking for. You need to know the frequency in hertz, you need to know the potential difference. So just learn these 2 numbers. It is a frequency of 50 hertz, and the potential difference is 230. And you have to be exact with the numbers on that. Now, question 5.2, nice maths question here. It's worth 4 marks. So the vending machine identifies the value of the coin by measuring the resistance of that coin. Now the power dissipated by the coin is 340 milliwatts when the current in the coin is 0.7 amperes. Calculate the resistance of the coin. So we need to calculate resistance, and we've got a current and we've got power. So we're looking at one of the four power equations. In this case, we need to be using power equals current squared multiplied by resistance. Now, again, you need to get a little bit savvy about this. This question is worth 4 marks. So we need to be doing a little bit of work. You should be suspicious about some kind of conversion. And hopefully you've picked up on the idea that there's 340 milliwatts. Now there's 1,000 milliwatts in a watt. So we need to use our standard units, so we need to convert it into watts. So we divide 340 milliwatts by 1,000, which means that there's 0.34 watts. We've got a mark just for doing the conversion. So substitute the numbers in. You've got 0.34 equals 0.75, but remember we need to square it, multiplied by resistance. Resistance is what we need to be trying to find out. We've got a second mark there. Our third mark is for making R, the resistance, the subject of the formula. We need to divide by the 0.75 squared, both sides. So you end up with 0.34 divided by 0.75 squared. Put those numbers into your calculator and you're going to get a resistance of 0.6 ohms. Nice 4 marks. And the important thing there is to be able to find the equations quickly. You do have the equations sheet. It's just a case of practicing and making sure you can find things. Alright, so question 6.3. Coins that are dirty are not recognized by the vending machine. Suggest one reason why. Well, if you think about it, the dirt is going to be covering the coin, so it's going to affect some of the charge flowing through that coin. So basically, to get your mark, you need to be talking about the fact that the dirt changes the resistance of the coin. That layer of dirt basically just interferes with it, and that's all the detail you need to give to get the 1 mark there. Alright, and then this is a circuit symbols question. We've got a circuit diagram here. It shows part of a different circuit used to monitor the temperature inside the vending machine. The circuit symbol for a thermistor has not been included. We've got to draw it. Now a thermistor is a type of resistor, so that's why we need that rectangle. Got the connecting wires either side. Now thermistor is that one which has that funny looking tick through it. That's the only acceptable answer to get 1 mark. Remember, do that one in pencil just in case you make a mistake, and it's much easier to correct. Okay, question 5.5. We've got a really kind of meaty maths question here because this one's worth 5 marks. So we've repeated the circuit diagram just to help you answer this question. Now we've also got a graph, so there's quite a lot to do here, quite a lot involved in our 5 marks. Now the cooling system inside the vending machine turns on when the temperature of the thermistor is above 20 degrees centigrade. Remember, a thermistor, resistance changes as the temperature increases. Determine the potential difference across the thermistor when the temperature is 20 degrees centigrade. Use the physics equation sheet. Now, the first thing we need to do on this is we need to work out what is the resistance of the thermistor at 20 degrees centigrade. And this is where we need to use your graph. So you would draw your ruler up onto the graph, and then you would draw across. Now you're going to have a ruler, so you've got a massive advantage over me. Now, read off the scale carefully. Now, by my reckoning, that is 80 ohms. So we've got 80 ohms of resistance across our thermistor. So just write in 80 ohms. Now, the important thing for this is we've also got a fixed resistor within our circuit. So it means that the total resistance, our total in our circuit, is going to be 400 ohms plus the 80 from the thermistor. So we've got a total resistance within the circuit of 480 ohms. Now, this is where we're going to use our good friend V equals IR, because we need to calculate the potential difference across the thermistor. So why are we going to use V equals IR? Well, we've got to work out V, that's potential difference. Now, we've got the total resistance there. So, and we've also got the potential difference of our battery, our power pack, I should say. So we can use V equals IR to work out the current within that series circuit. And remember, the current is going to be the same at any point within that circuit. So it'll be the same current going through the 400 ohm resistor as it is through the thermistor. And that'll become important. So to work out the current flowing in the whole circuit, we've got a potential difference of 12 equals I times this total resistance of 480 ohms. That means that the current, we need to divide both sides by 480 to get I by itself, is 12 over 480. Put that in your calculator and we've now got a current throughout that whole circuit of 0.025 amperes. Alright, we now need to work out the current, so the potential difference across the thermistor within our circuit. So again, we're still using V equals IR, but this time V is the unknown bit. So you got V equals 0.025 amperes multiplied by the resistance of the resistor, which is 80. Put those numbers into your calculator and you're going to calculate 2.0 volts. And there's your 5 marks. So there's not a huge amount of writing in that to get your 5 marks, but there's quite a lot of physics in it. And it's just making sure you understand your rules of electricity. Well done if you got 5 marks in particular on that question, and well done if you got the full 13 marks on that particular question. Alright, moving on to question 6. So we've got a ride at a theme park and a person is strapped into a pod that is attached to 2 stretched bungee cords. Now we're being told here the bungee cords behave like springs. So below we've got the person using the ride and you can see the bungee cords are stretching as the person drops down towards the ground. Which energy store increases as the bungee cords are stretched? So of course this is our elastic potential store increasing, and really that's the only acceptable answer on that one. Right, so then on 6.2 we need to do a bit of math. So when the pod is released, the pod accelerates upwards. Before the pod is released, the extension of each of the 2 bungee cords is 8 meters. The spring constant of each bungee cord is 735 Newton meters. Now we've got the mass of the pod, which is 240 kilograms, and the question is always going to give you gravitational field strength, which is 9.8 newtons per kilogram. We've got to calculate the maximum height reached by the pod. And again, it's telling us to use the physics equation sheet. Now, first thing we need to think about is trying to calculate how much energy, how much elastic energy is going to be stored in our bungee rope. So you've got E equals half K, that's the spring constant, multiplied by the extension squared. Now we just need to substitute our numbers in to calculate that value. So you've got a half times 735 multiplied by, it's not just 8, it's 8 squared. From there, put those numbers in your calculator, you should come up with a value of our elastic potential energy of 23,520 joules. Now, remember, this is just stored in one of the bungee cords. There are 2 bungee cords. So our total energy, so the total elastic potential is going to be 47,040 joules. All I've done is multiplied 23,520 by 2. Now, we need to work out the maximum height. So we need to assume there's a 100% conversion of that elastic potential energy into the gravitational store of energy. So that's where EP equals mass times gravitational field strength multiplied by height. So we need to substitute in the numbers we've got. I'm just going to go up to the side here. We've got a bit more space. So you've got 47,040 joules equals the mass. The mass is given at the start of the question, which is 240 kilograms. Gravitational field strength, always given to you, 9.8, multiplied by the height, by h. That's the bit we don't actually know. We then just need to do a bit of rearrangement. We need to get h by itself, make it the subject of the formula, and so we end up with 47,040 divided by the 240 multiplied by 9.8. Again, just put the numbers carefully into your calculator, careful with your brackets at the bottom here, and you end up with a nice round figure of 20 meters. So well done if you got that answer. Now, if you didn't double your answer to get the total elastic potential energy, you could still get 5 out of the 6 possible marks. You just lose a mark for not doing that step, so that error would be carried forward. But this one is a nice one. Just think about the question, the fact that there's two bungees involved in this particular thing. That's why we're doubling that elastic potential energy. Okay, now on 6.3, the actual maximum height reached by the pod will be lower than the correct answer that we calculated. So it's going to be less than 20 meters. We need to explain why. And of course, this is all to do with unwanted energy losses. So anything moving, there's going to be drag or air resistance. So air resistance will oppose the upward motion of the pod, which means, therefore, not all of the elastic potential energy, so that's EE, gets converted into the gravitational store of energy. So that's why you're never going to hit that maximum height of 20 meters. Now that whole question is worth 9 marks. Well done if you got 9 on that one. There's some good kind of maths questions in it, so well done if you did get those marks. And then question 7, we've got the figure showing a measuring cylinder containing some water, which a student used to measure the volume of a metal ring. So the first question is asking, when measuring the volume, the student's eye was in line with the level of the water. Which type of error would have been caused if the student's eye was not in line with the line of the water? Because this is basically a human error that gets covered by your random error, and that's where you get your mark from. It's always worth checking what your errors. You're always going to get an errors question somewhere within the 6 papers. All right, and then 7.2, the student tied a piece of thick string to the metal ring and lowered the ring into the water. Suggest one reason why the student should have used thin string instead. Now this is only worth 1 mark. Obviously the thinner string would have less of a volume than the thicker string, therefore it would have less effect on the actual volume. So thinner string affects the volume, the total volume, less. Obviously, the thinner string is still going to affect the volume. It's going to increase the actual volume, but not as much as our thick string would have done. Okay, so we've got some results now in our table, and 7.3 is asking us, or telling us that the true volume of the ring was 0.44 cubic centimeters. Even without using the string, the measuring cylinder could not give an accurate value for the volume of the ring. Give a reason why. And again, this is just worth 1 mark. Now, the measuring cylinder, if you go back to the diagram, doesn't go down to 2 decimal places. The resolution of the measuring cylinder is only 0.2 centimeters cubed. So the resolution isn't high enough on our measuring cylinder. So I would talk about resolution not being high enough. And if you go back and look at that measuring cylinder, the resolution is 0.2 cubic centimeters. So you can't make any measurements smaller than that value in 0.2 of a cubic centimeter. Okay, so question 7.4, the student used a balance to measure the mass of the ring. After the ring was removed from the balance, the reading on the balance was 0.02 grams. How can the student use the readings from the balance to determine the correct mass of the ring? Now, clearly this is a zero error. Now, if you talk about a zero error, you're not going to get the mark. What you need to do, and this is what it's saying, how can we use the value given to get the right answer? We need to subtract 0.02 grams from the measured value. And that will give us the correct mass. Right, and then we've got a nice little maths question again. So we're looking at, the student determined the density of the ring was 21,500 kilograms per meter cubed. The volume of the ring was 0.44 cubic centimeters. Calculate the mass of the ring. Use the physics equation sheet, give your answer in kilograms. So this is where we need to do a little bit of converting. We've got the volume in 0.44 cubic centimeters. We need that in cubic meters. So we need to divide by 100 times 100 times 100, which would give us, we need to divide by 1,000,000 to turn 0.44 cubic centimeters, and that will come out, and I'm going to write this in standard form, save having to write lots of zeros. It's going to be 4.4 times 10 to the minus 7 meters cubed. Now that's your first mark kind of earned. Remember, this is 4 marks just for using one equation, so there's always going to be a conversion in there. Now if you remember, density is mass over volume. We've got a density of 21,500. We need to find out the mass. That's our unknown. And we've got the volume of 4.4 times 10 to the minus 7. We need to get the mass by itself, so we multiply both sides by 4.4 times 10 to the minus 7. So we end up with mass equals 21,500 multiplied by 4.4 times 10 to the minus 7. When you put those numbers into your calculator, you will get 0.00946 of a kilogram, or you might keep it in standard form, 9.46 times 10 to the minus 3 kilograms. Now that density question is out of 8. Well done if you got all 8 marks on that one. So question 8 is all about pressure. So a student is investigating how the pressure in a fixed mass of air varies with the volume of that air. So we've got our syringe connected to a pressure gauge. Now 8.1, when the plunger was pushed slowly into the syringe, the pressure in the syringe increased. The temperature of the air remained constant. Explain why the pressure increased. Well, first of all, you're pushing the air particles closer together. So that's going to be our first mark. So it means that the frequency of the collisions between the air particles, between particles and the walls, increases. So basically, our particles have got less room to move, so they're more likely to crash into the sides of the syringe. And it means that therefore a larger force is being exerted over a smaller area. Therefore, the pressure goes up. And there's your 3 marks on that one. So now we've got a fire piston, and it's a special type of syringe that can be used to start fires, and we've got a diagram of it. So the plunger is pushed quickly downwards and compresses the air. When the air is compressed quickly, the temperature of the air increases. Now question 8.2 is asking us, how does an increase in temperature affect the air particles inside the piston? Remember, increased temperature, our particles are going to move more, which means that their store of kinetic energy goes up. So without even looking at the second or third answer, it is clear that the right answer is that top one. The mean kinetic energy of the particles increases. Question 8.3. Now we're into a bit of a calculation here. So when the air is hot enough, a small piece of cotton wool in the piston catches fire. The energy transferred to the air in the piston is 0.013 joules. We're given the mass of the air in the piston, and you're given the specific heat capacity of air. We need to calculate the temperature change of the air. Use the physics equation sheet. So here, if we're talking about specific heat capacity, you're talking about energy equals mass times specific heat capacity multiplied by the change in temperature. Now, they're a bit sneaky here because they've given you the energy in joules. However, they've given you the specific heat capacity in kilojoules. So the first thing you need to do is to convert that 1.01 kilojoules into 1010 joules per kilogram degree C. Now, bear in mind this is worth 4 marks. And there should be a bit of a hint there that we need to do a conversion. And that's the mark we're going to get for doing the conversion. We now need to substitute in the numbers that we've got. We've got the energy 0.0130 equals the mass. Now the mass is a tiny number, so it's 2.6 times 10 to the minus 8. And then that's multiplied by the specific heat capacity, which we've now established is 1010, and it's a change in temperature that we need to find, so the delta theta. We don't just need to do some number crunching, so we've got another mark substituting in the numbers correctly. That means that the change in temperature equals 0.013 divided by the 2.6 times 10 to the minus 8 multiplied by 1010. So we're now up to 3 marks from that, and then all you need to do is put those numbers into your calculator, and you're going to end up with a change of temperature of 495 degrees centigrade. So you should technically write in the answer there. So it's a nice question for 4 marks. Again, it's just making sure that you're suspicious about conversions and you also remember to be able to use how to use standard form. So well done if you got the 4 marks on that one. Okay, then question now, we're back on to radioactivity. So a teacher investigated the radiation emitted by 2 different radioactive sources. So we've got A and B. So figure 14 shows a radiation detector positioned near one of the radioactive sources. So that's how they did it with your Geiger Muller tube, with a Geiger counter. You've got your detector and you've got your radioactive source. Now the teacher measured the count rate at different distances for each radioactive source. And that's where that graph comes from. So you've got the dashed line is for source A, and then you've got the solid line for source B. And it's count rate in counts per minute, and it's distance in centimeters from your detector. So 9.1, explain how figure 15 shows that source A only emits alpha radiation. Well, if you look at source A, that's a dashed line, well, it suggests that the radiation only travels about 3 centimeters. Maximum of 3 centimeters, only travels 3 centimeters. Now, after that, so after 3 centimeters, you're just back to the background level, back to the background count. So that means there's nothing being detected from that source. And the final bit is to remember that alpha radiation has a short range, very short range in air. And that's actually your 3 marks. So nice straightforward one just to start you off with. Now 9.2, figure 15 cannot be used to determine if source B emits beta radiation or gamma radiation. Explain how an absorbing material could be used to show which type of radiation is emitted by source B. Now, what we need to use a material that is going to block beta, but obviously allows gamma to go straight through it. You should be thinking aluminium. So use an aluminium sheet, and the explanation is beta can't penetrate, but gamma can. So if you still have a count rate after the aluminium sheet is put there, it tells you that the radiation is gamma. If the aluminium sheet blocks the radiation, then it's telling you that it's only beta. So good application of your knowledge of alpha, beta, gamma there. And then 9.3, a little bit about safety. The teacher took safety precautions during the experiment. Suggest one safety precaution the teacher would have taken to reduce the radiation dose the teacher received. Well, there's only 1 mark, so you just need to make 1 point. So the best way is to increase the distance between the source and the teacher. Another good one is limit exposure time. You could use tongs and forceps. You could wear a lead apron, which probably is quite expensive, so it's probably not practical in school. Stand safely behind a safety screen. So there's lots of kind of common sense things away. Point the source away from the teacher as well could be another good one. All right, 9.4, another 1 mark question. Suggest one safety precaution that the teacher would have taken to avoid becoming contaminated. So contaminated is when you get material, radioactive material actually on yourself. So you could wear gloves or an apron, use forceps, handle the sample with forceps so it's not coming anywhere near your skin. Anything sensible like that, and you get yourself a mark. Okay, so question 9.5. This time we've got a graph showing the number of atoms of a radioactive element in a sample varied with time. So you've got the number of atoms, and then you've got the time in seconds. Activity is a rate at which a source of unstable nuclei decays. Determine the activity of the radioactive sample at 300 seconds, give the unit. Now, this was the first time I've seen a question like this come up, and you need to mark on at 300 seconds. Now, you need to draw a tangent because this is clearly not a straight line. Now, it's much easier for you to do this because you can use a ruler. It's a bit trickier with the computer. So you've got your tangent there, and the way to do it would then be to draw your big triangle. So I would go something like this, and that's quite close to it. So remember, this bit here is your change in Y, and it's this bit here is your change in X. So in this case, activity the change in y divided by the change in x. Now, you'll be able to do this much easier on kind of paper at home, a bit harder on the computer screen. But what you should end up with is a calculation, a gradient of 7.1 times 10 to the 20, or the activity should come out as 7.1 times 10 to the 20. Now, they will give you credit for anything between 6.5 and 7.6 times 10 to the 20. So that activity should go in there. And this caught out a few people when it came up. We measure activity in becquerels. So it's either capital B, lowercase q, or the full becquerel gets you a mark in itself. So if you didn't answer anything, but wrote in the unit correctly, you've got a mark. Now that question, probably one of the tricky questions on radioactivity, that's worth 11 marks. So, in particular, well done if you got 11 marks on that one. Okay, we're now into the final kind of question of the paper, and it's quite a nice question because we're back on electricity again. So we've got the live wire in a 3-core cable is connected to a fuse inside a plug. A fuse contains a wire that is designed to melt when the current gets too great. And here we've got the picture of a fuse with our thin piece of wire inside the fuse that melts. Nice starting point. 10.1. What colour is the insulation covering the live wire? Remember, there is only one answer. It's brown. Draw the circuit symbol for a fuse in the box below. This one, I suppose it's a type of resistor, which is why we still keep our rectangle. And we've got a line which goes all the way through the rectangle. Think of it as that being the fuse wire being drawn in. And that's worth 1 mark. Now we've got a couple of maths questions now. So 10.3, the fuse wire melts when there is a charge flow of 2 coulombs for 400 milliseconds. Calculate the current in the fuse wire. Again, we should be getting good at this. This is worth 4 marks. Now we're just using one formula. Think about current, charge flow, and time. So we've got charge flow Q equals current times time. Q equals IT. Now you're thinking, why do we get 4 marks? Well, by now you should be suspicious and thinking of conversions. We've got 400 milliseconds. So the first thing we need to do is to convert those 400 milliseconds into 0.4 of a second. Remember, there's 1,000 milliseconds in 1 second. We now just need to substitute in the numbers we've got. So we've got 2 equals, we don't know what the current is, I times 0.4. I therefore is going to be 2 divided by 0.4, which gives us a current of 5 amperes. So in this case, the numbers are relatively straightforward. And then 10.4, another 4 mark calculation. When the fuse wire is at its melting point, the additional energy needed to melt the wire is 1.02 joules. We're being told the specific latent heat of the fuse wire is 60 kilojoules per kilogram. We've got to calculate the mass of the fuse wire. Right, so again, this is worth 4 marks. There's a few clues here. We're talking about melting the wire, so we're thinking about changing state. So that means we need to use E equals ml. Energy equals mass times the latent heat, specific latent heat. Now, we're being told that the fuse wire, the latent heat of the fuse wire is 60 kilojoules per kilogram. We've been told how much energy it takes to melt in joules. So again, 4 mark question, we've got a conversion to do. 60 kilojoules equals 60,000 joules per kilogram. So we've got 1 mark for doing that conversion. Let's substitute in the numbers that we've got. So we've been told 1.02 joules of energy equals mass times 60,000. 1, 2, 3. Be careful with these zeros. We need to make mass the subject of the formula, so we divide both sides by 60,000. So we end up with mass equals 1.02 divided by 60,000. Put those numbers in your calculator and you're going to get a very small number, and it's going to be in standard form. So it's 1.7 times 10 to the minus 5. Doesn't matter if you write that as a full number, because it doesn't specify whether it wants a full number or like a decimal number or standard form. Whichever way it comes up in your calculator, just write that out. All right, and then the final question. So 10.5, the calculation in the previous question assumes there was no energy transferred to the surroundings. How would the time taken for the wire to melt be affected if some energy was transferred to the surroundings? We also have to give the reason for the answer. So if we are losing energy, not all that energy is going into melting the wire. So the time taken would increase. And the reason is more energy would need to be transferred. I'm not quite sure what's happened to my pen at the end there. Right, so you only get the second mark if you get the first mark right. So clearly the reason has to explain the correct answer, and that's worth 2 marks in total. That question is worth 12, some nice maths ones in there, nice way to finish the paper. Well done if you got 12 out of 12. You now need to add up your total score out of 100. Well done if you got 100.